Students, I have told you the simple pendulum, compound pendulum, and then the pendulum of infinite length, and the fourth was the tunnel dug through the earth. So, the time period of the body which is allowed to fall in the tunnel, that will execute the SHM and it will not go out of the tunnel, and this time period will be 84.6. So, the time period of the infinite length of the pendulum, and that the body which is moving in the tunnel across the earth will have the same time period. And now I am going to tell you about the time period of a body suspended with the lower end of the vertical spring. This is now fifth case. Time period of a body suspended at lower end of vertical spring. I will take this of there's the horizontal spring also. Let L equal to length of ideal spring. So, what is meant by ideal spring? Ideal spring means the spring that have that it has the coefficient of elasticity to be very large, so that it can move in the vertical plane, and also the spring is taken to be very mass of the spring is approximately 0. So this is the massless spring, ideal spring or massless spring. Let us suppose that this is a spring. Its length is L, and then it is suspended. This is the mass mg, and it will have a force vertically upward, restoring force. And this is given a displacement by, then even the restoring force will act vertically upward, and it will have the weight vertically downward. So the restoring force F equal to minus Ky, and the time period T equal to 2 pi square root of m upon k. This is for the single body which is suspended with the vertical spring. And if suppose this is the one position, this is now one position, and now second is series combination of springs. Series combination is how that this is suppose like this, and there is another spring like this. This is two like this. Then this is now force constant K1, this is now force constant K2. Then in this case the effective force constant force constant 1 upon K equal to 1 upon K1 plus 1 upon K2. So this K equal to K1 K2 upon K1 plus K2. And now the time period. Therefore, time period T equal to 2 pi square root of m upon, this is now your K1 K2 into K1 plus K2. This is so much. So if suppose there are n springs which are attached, from n springs K equal to K1 plus K2 plus K3 plus and so on, this is now Kn, and let K1 equal to K2 equal to K3 equal to and so on equal to K dash, then K equal to n K dash. So K dash equal to K upon n. Therefore time period T dash equal to 2 pi square root of m upon K upon n. So this is equal to 2 pi square root of m upon K into n. This is not T dash. So this T dash equal to T root n. Now time period will increase. As you can see that the total of one part will be take, then the time period of the single piece will increase. This is now series combination of springs, and now I take the parallel combination of springs. Parallel combination of springs. Now in parallel combination is what, that if we have the spring suppose like this, and this is a single mass which is attached to this one, or we have the spring like this. This is a mass, and this is now second spring, This is the fourth constant K1, this is K2, it is K1, this is now K2. Also, if we have on a horizontal surface, this is so much, this is the frictionless surface. Frictionless surface. Then all these are the parallel combination of the springs. So in case of parallel combination, we have this K equal to K1 plus K2. This is the effective K. Effective force constant. And therefore time period, this T equal to 2 pi square root of m upon K1 plus K2. This is like this. Let n springs are in parallel, then K equal to K1 plus K2 plus K3. If K1 equal to K2 equal to K3 equal to and so on equal to K, then K equal to Nk dash. So time period, T equal to 2 pi square root of m, and now from here this K dash equal to K upon n, K upon n. So this is equal to 2 pi square root of m upon K, this T dash. So T dash equal to T root n. Now there is a modification in the series combination. Modification in series. There I told you like this, but actually this is not so. There I have this 1 upon K equal to 1 upon K1 plus 1 upon K2 plus 1 upon K3 plus and so on 1 upon Kn. Then for K1 equal to K2 equal to K3 equal to and so on, this is equal to K dash. Then 1 upon K equal to, this will be your n upon K dash. So this will give you the K dash equal to K upon n. K dash equal to Nk, equal to Nk. So this time period t equal to t dash equal to 2 pi square root of m upon, now here we will use this nk, so this is equal to 2 pi, then you can see from here that this t equal to upon root n, so this t dash equal to t upon root n. So this you modify, where I told you about the in the series in the parallel combination. In parallel combination I told you like this one, but that was the wrong one. So you please have this 1 upon k equal to 1 upon k1 plus 1 upon k2, and then time period will come out to be like this one. So when the n springs are connected in series, then the time period decreases. When n springs are connected in parallel, then time period increases. So this is about the spring, and now we are having now third case. If a spring is divided in n equal parts, then force constant of each part will be nk. So if suppose this is in two parts, then this new force constant k dash equal to nk. N times suppose the spring is divided into two parts, then each part will have a force constant of 2k. If divided into three equal parts, then the force constant will be 3k. So this is the n times of the initial value of the force constant. So thus when the spring is divided into the equal parts, then their force constant increases by the parts which are made from the spring. Two parts, then the 2 times, then 3 parts, then 3 times, 4 parts, then this is now 4 times. So this is what the oscillations of the simple the body attached at the lower end of the vertical spring or the horizontal spring. So for both we are having this the time period. So this is about the spring, the motion of the body attached to the spring. So you all like, share and subscribe this video. Thank you.